today we're going to begin our unit on proportional reasoning. Now, proportional reasoning starts in elementary school when children start making comparisons about quantities. In lower grades, we focus on, is this set bigger or smaller than the other set? As students get a little bit older, we make more descriptive comparisons of quantities. That's 2 more or 2 less. But 2 more or 2 less can be very different. If I said 2 more than 2, well, that's 4. 2 more than 2 is 4, okay? But 2 more than 4, well, that's 6. Well, 4, while it's 2 more, is also 2 times as big as 2. Whereas 6 isn't twice as big as 4. 6 is 1.5 times as big as 4. So, as our understanding of math and numbers and those relationships between quantities change, so does the way we compare them. So proportional reasoning is the idea that the relationship between 2 numbers is multiplicative. Okay, so that is the new level of precision that kids use at this level when they compare quantities, is the multiplicative relationship between 2 quantities. So how does that progress? We view proportional reasoning as a pivotal concept. On one hand, it is the capstone of a child's elementary school arithmetic, and on the other hand, it's the cornerstone of all that is to follow. So let's talk about that. So when does proportional reasoning begin? Probably in the middle elementary grades or even younger grades, when we start looking at patterns, we're starting to develop those relationships about proportionality. Okay? Especially about 3rd grade when we start thinking about multiplication and division. So that's when the ideas around proportionality begin, is with the development of multiplication and division. Now, proportionality is formally introduced in the 6th grade. And we really spend a lot of time in the 6th grade and throughout middle school developing the idea of proportionality, because it is the cornerstone of much of the math to follow in high school. Proportionality gives us slope. And slope is slope of a linear function is the foundation of Math 1. It's what we compare all other functions to. So slope is a huge piece of future mathematics learning. In algebra, in geometry, kids will work with similar figures, and the relationship between similar figures is that they are proportional. And then lastly, when students get into advanced math classes, Math 3, they're going to work with trigonometric functions, and each one of those trig functions is a ratio between the sides in a right triangle. So proportionality is a huge piece of what students will work with from middle elementary grades through the rest of their mathematics career. So let's look at this problem. If Sam can mow 1 lawn in 2 hours, how many lawns can he mow in 8 hours? This is a pretty standard proportion problem that you would see in middle school. So take just a second, and I want you to write a proportional relationship that would represent this situation. And if you get one, can you maybe come up with another one? What are some different proportional relationships you can come up with? Okay, so you might say that Sam can mow 1 lawn in 2 hours. So how many lawns can he mow in 8 hours? How many of you have that one? Okay, who has a different one? Oh, 1 lawn in 2 hours is the same thing as how many lawns in 8 hours? Would that work as well? Anything else? What you can find is, if we take this proportion we simply rotate it, we get the different proportions that are possible. So if you can imagine that, that's the 2 to 1. We can flip it over this way. 8 hours is to how many lawns as 2 hours is to 1 lawn. There are many different proportions that will work that represent this situation. However, there are some that would not work. Can someone give me a non-example? An example of a proportion that would not work? Well, let's see. Let's see. Let me get rid of mine and let's look at some that they have. So there's the 1 is to 2 as x is to 8. Here we have 2 hours is 1 lawn as 8 hours is to how many lawns? 2 hours is to 8 lawns as 1 hour is to how many lawns? Now let's look at this one. If I can do X lawns in 8 hours, that's equivalent to 2 hours to 1 lawn. Now do you see anything different about that one? What you have to bear in mind is the equivalence relationship that they gave you in the beginning. He can mow 1 lawn in 2 hours. Okay? Now, you might also notice that even though we're doing math, there's a lot of words up here. I think the labels are very important when you set up the relationship. So, here's my 1 to 2. 1 lawn, 2 hours. 1 lawn goes with 2 hours. 1 lawn, 2 hours. Well, we have the 1 lawn and 2 hours here, but if we compare lawns to hours, then on this side, I also have to compare lawns to hours. So that's why this one is incorrect, because it doesn't keep the same comparison of units. What's very interesting about this slide is that in Math Foundations, we're choosing to try to do things in a different approach. So very rarely have we ever looked at a concrete pictorial view of a proportion. And that's what this is. So this demonstrates that Sam can mow 1 lawn in 2 hours. Now, we've represented it with the division bar so that it looks like a fraction, and a student might bring that up. So you would have to have a conversation about the difference between ratios and fractions, and how a ratio is just a comparison of 2 quantities. Okay, we're comparing the amount of the fact that he can mow 1 lawn in 2 hours, so we're making that comparison. Whereas a fraction is a comparison, but it's a part-to-whole comparison. This is a part-to-part comparison. So while it might look like a fraction, it's a ratio. So emphasize that vocabulary when you're talking to this about students, if students bring up the idea of a fraction. So what we're going to do now is we're going to look at what happens as we expand the ratio. So here is 1 lawn in 2 hours, and I can represent this pictorially. Okay? So I want you to look at this illustration, and I'm going to ask you some questions. How many hours would it take for Sam to mow 2 lawns? How can we use this pictorial representation to answer that question? Well, 1 lawn took 2 hours. 2 lawns is going to take all 4 of those hours. Okay? My next question for you is, if Sam mowed for 6 hours, how many lawns did he mow? Well, let's look. So my hours are here on the bottom, so 6 hours would be all the way across, so that means he could mow all 3 of the lawns. So just a different approach, a more concrete approach to help your students make this jump to something that's pretty abstract. So start concrete and then you can make it more abstract as we go along. Now, I want to introduce this idea of a T-chart or a table. Okay, so we're going to be looking at, well, keeping the comparison of our lawns and hours. We're going to do this pictorially. So we have 1 lawn in 2 hours. Okay, there's the 1 lawn in 2 hours, but I'm going to extend it. So now I have 2 lawns in 4 hours. Okay, here we go, extending it again. 3 lawns in 6 hours. 4 lawns in 8 hours. So you could even go from this phase to having students write a more traditional T-chart where 1 is 2, 2 lawns is 4 hours, 3 lawns is 6 hours, 4 lawns is 8 hours. Okay? Just a different way for students to organize their information. So this is the double number line method of proportions. So why do we need 2 number lines? Well, we need 2 number lines because we're comparing 2 quantities. So the top number line is representing the lawns that we're mowing, and the bottom number line is representing the hours that we spend mowing the lawns. Okay? So let's think about what that would look like. We know that 1 lawn would take 2 hours. 2 lawns would take 4 hours. 3 lawns would take 6 hours. 4 lawns would take 8 hours. This model allows you to see some other equivalent ratios. For example, what if I wanted to know what I could accomplish in 1 hour? Well, where is 1 hour? Well, 1 hour is right here. Right? That's 1 hour. So what would correspond with that here? That would correspond here, which would be half a lawn. So in 1 hour, I could mow half a lawn. So that's kind of a different approach. Okay. So now, if I take this double number line approach and I rotate this particular number line counterclockwise, what's going to happen is I'm going to get the coordinate plane. So that's going to be a different way to represent this proportional relationship. We can plot, so here's my lawns, and here's my hours, and we can plot those relationships on the coordinate plane. So this dot would represent that in 0 hours, I mowed 0 lawns. 1 lawn in 2 hours. 2 lawns in 4 hours. 3 lawns in 6 hours, and so on. Okay, so this is an example of what that would look like. Now notice that this is an example of a linear function. Okay, our lines, and this is also a direct variation because we're going through the origin. So this is an example of proportionality. Notice that each ordered pair represents that comparison of 2 quantities. This point right here would represent the fact that I can mow 1 lawn in 2 hours, that I can mow 2 lawns in 4 hours. So it's still a comparison of 2 quantities. Now, let's get into the 2 types of multiplicative relationships. We're just going to keep going. So there are two types of multiplicative relationships that exist or that students will recognize when they are working with proportional relationships. Okay? The first one is this idea of a scalar multiplicative relationship. And this is when we look at things like scale factor, and we're looking across situations. We're going to be comparing units. Okay, so let's look at this. So, if I start with this situation, 1 lawn in 2 hours, what happens to go from here to here? What did I do? I multiplied by 2. Okay? So, does that same relationship exist here? When I go from 1 lawn in 2 hours to 2 lawns in 4 hours, did I in fact multiply by 2? Okay? I multiply my lawns by 2, and I multiply my hours by 2. Now, we're going across a different situation. I'm going to go from this initial 1 lawn in 2 hours to this situation. So, what did I do to the 1 lawn to get the 3? Well, that time, I multiplied by 3. Does that same thing exist here? Did I multiply my hours by 3? So does that make sense? That's that scalar relationship. I am comparing my lawns to lawns, my hours to hours, and the multiplicative relationship that exists there. Now, let's look at the double number line. From 1 to 2, I'm doubling. And from 2 to 4, I'm doubling. From 1 to 3, I'm tripling. From 2 to 6, I'm tripling. So I'm comparing lawns to lawns, hours to hours. Okay? We can even see that in our work with the coordinate plane and the ordered pairs. So, this one's a little strange to look at, so let me see if I can grasp it. So, I'm comparing, so, if I go from 1 to 2, okay, that's timesing by 2. If I go from 2 to 4, I'm timesing by 2. If I go from here to here, whoops, I should change the blue since I've been following that pattern. If I go from here to here, that is multiplying by 3. And if I go from here to here, I'm timesing by 3. Likewise, if I want to follow it out to this one, from my original one out to here, whoops, out to 4, that would be timesing by 4. So 2 times 4 would give me 8. So that is an example of the scalar multiplication relationship. The second kind of relationship is a little bit more advanced, and it's the functional relationship. And this is the relationship that really gets to students when they start into algebra in Math 1, where they're looking for the relationship between the two quantities. So it's an internal multiplicative relationship, the relationship that exists between the two variables. So we're looking for what's the relationship between the lawns and the hours. 1 lawn, what do I do to the number of lawns to get the number of hours? 1 times what gives me 2? 2. Okay? 2 lawns in 4 hours. 2 times what gives me 4? 2. 3 times what gives me 6 times 2. And you guessed it, 4 times what gives me the 8? 2. This constant, the fact that I'm multiplying by the same value every time, is what leads students to slope when they get into 7th, 8th grade in Math 1, developing that idea of slope. But notice that it's the relationship across, the relationship between lawns and hours. So when we look at it this way, on the double number line, we're not looking across a situation, we're looking between. So what's the relationship between 1 and 2, 2 and 4, 3 and 6, 4 and 8? What's the multiplicative relationship? 1 times what gives me 2? 1 times 2. 2 times what gives me 4? 2 times 2. 3 times what gives me 6? 3 times 2. So it's that internal multiplicative relationship between the two variables. We're comparing the two variables to each other. Okay, so now we're back to our coordinate plane again. So what's that relationship? This is where the idea of slope comes from. Okay, this is a 2 to 1. That for every time I increase the number of lawns, I'm increasing the hours by 2. Okay, it's that 2 to 1 relationship that exists every time. And we call these slope triangles. They're really, we can actually draw different kinds of triangles here, and students can see that they're similar. Okay, but it's this idea of for every 2 hours, I get 1 lawn. 2 hours, 1 lawn. Okay, you can also see it in your ordered pairs. 1 times 2 is 2. 2 times 2 is 4. It's that relationship. So let's just review a little about the difference between scalar and functional relationships. In a scalar multiplicative relationship, you are comparing across situations. You are comparing like units. What do I do to my lawns to get to my next lawns? And that relationship should be the same as the hours to the next hours. Okay? We're comparing lawns to lawns or hours to hours. Whereas in the functional relationship, recall, we're making that comparison between the lawn and the hours. We're going across units. 1 lawn in 2 hours. Here's a nice Venn diagram. What they have in common is that the relationships are multiplicative. Okay? Scalar, like units. Lawns to lawns, hours to hours, different situations. Whereas our functional is that comparison of unlike terms, the relationship between lawns and hours. Okay? This one, and this idea of unit rate, what can you do in 1, is really big in Math 1 especially. Now, let's practice. So I've given you a real life situation. I've got a picture here. The original picture is 5 inches by 10 inches. And we're going to enlarge it. And all I know about the enlargement is that it is 15 inches across. What is the height or the width of the picture, depending on your interpretation? Okay? So try to solve this using a functional approach and try to solve this using a scalar approach. I'll give you just a second to do that, and then we'll discuss the two differences. Okay, so let's start with a proportion that would be functional. Okay, so I know that what's the relationship between my length and my width. What can I do to 5 to get 10? Well, that relationship is 5 times 2 is 10. Okay, that's the functional relationship. So I have to maintain that same relationship. So if 5 times 2 is 10, 15 times 2 gives me what? 30. Now let's look at that proportion. 5 inches to 10 inches, this is my length and my width. Okay, my length is 15. Okay, so what is my height? So we're looking this way. 5 times 2 is 10. So 15 times 2 is 30. Okay, that's the functional approach. Okay, now let's think about it a different way. Let's think about it using the scalar approach. We know what the answer should be. Remember, the scalar approach is going to say, I'm going to compare my length to my length and my height to my height. So 5 times what is 15? 5 times 3. So I maintain that relationship. So 10 times 3 would be what? 30. That matches the answer we got when we took the functional approach. Now let's look at it. So 5 inches to 15 inches. So this is a length to a length, and that's 5 times 3. 5 times 3 is 15, so that's going to be equivalent to my 10 inches, which is my height or my width. And since I have to maintain that equal relationship of multiplying by 3, that tells me that 10 times 3, that my height should be 30 in my enlargement. So that's how to use both approaches, the functional and the scalar, to do a problem that's proportional. Now, you're probably thinking, she didn't cross multiply and divide one time. And that's the point of this, is that if students arrive at that, that's fine, but we really want to emphasize this multiplicative relationship and the different ways they can view it before we try to force them into something about cross products and butterflies.